Okay, so we just use the Reynolds transport theorem to derive conservation of mass for the general case where we have some blob of a control volume and flow going in or out of it just at arbitrary spots. Okay, so that equation for the general case was 0 equals the derivative with respect to time times the integral, or not times, but of the integral over your control volume of rho dV. So basically, how is rho changing over your volume and then with respect to time as well, plus over our inlets and exits, which we usually abbreviate CS for control surface, so over the whole edge of your control volume of the integral of rho v dot n dA. And that integral rho v dot n dA was your m dot from before. All right, so we don't usually use this generalized equation. Usually we simplify it because we don't have rho changing all over our volume, and it's maybe not an unsteady problem, which would, we got this DDT term. So there's a lot of simplifications we can make. And the first one is fixed number of inlets and exits. So normally we don't have flow coming in and out every which way at the edges of our control volume. So for instance, in this problem, we have one inlet here at 3, and we have another inlet here at 1, and then we have one exit at 2. Right here in the middle, we don't have mass going in or out. No mass going in or out here. Okay, so just fixed spots in our control volume or on the edges of our control volume where we have fluid going in or out. Okay, so whenever we do these problems, by the way, be sure to number all your inlets and exits because you're going to use subscripts throughout your solution of your problems, 1, 2, 3, and I need to know what you mean by 1, 2, and 3. Okay, so again, what we can do with this, and it's part of our simplification for fixed inlets and outlets, what we're going to do is convert that integral over the whole CS is to basically a sum of integrals. Okay, and the other thing is we're going to already take into account the sign. So we know that at an inlet, V dot N is negative, and an outlet, V dot N, is positive, so we can go ahead and put in the signs, and then we can kind of drop the n's usually, as long as our velocities are all going straight in or straight out. Okay, so if we do that, we can say, okay, our simplified form is still this first term plus the sum of the m dot outs minus the sum of the m dot ins. Okay, that should be starting to look a little bit familiar from thermo. But what's different is our m dots. Our m dots are still integrals over, say, inlet 1, rho v dot n dA. And we put the absolute value signs around it just to say, okay, that's the magnitude. We've already accounted for the sign here with the negative sign at the inlets, for the inlets. Okay, so next simplification happens a lot, not always, but a lot of times we have steady flow. You got to remember what your definition is, steady flow. Look at it 5 minutes from now. Looks the same, steady flow. Mass isn't changing inside the control volume, in other words. Time derivative or any other property is not changing inside the control volume or at the inlets or exits. So for that case, the time derivative, which was that big triple integral with the derivative over the control volume, that whole term is going to be 0, yay. And what we end up with then is just the sum of the m dots in equals the sum of the m dots out. Now these m dots can still be integrals, but that does simplify it a lot. And that happens. Most of the time, it's going to be steady flow. Steady incompressible flow, fixed number of inlets and exits. Okay, incompressible again meant rho equals constant. Okay, and if rho equals constant, it can pop out of the integrals. So let's pull it out of our integral here. And what we get is rho, m dot is rho times the integral v dot n dA. Well, that's just rho times q. Okay, and that's going to be on both sides of this equation, so we can cancel the rows out, and you just get the sum of the Q in equals the sum of the Q out. Again, Q was our volume flow rate, and our volume flow rate was the integral of V dot N dA, or if it's average velocity, which we get down here, that's just going to be V times A. So Q equals V times A, M dot equals rho VA. So what we mean by this versus this, or our integral kind of form versus our average velocity method, is maybe in the real case, say it's a pipe, we're going to get a velocity profile that really, in reality, looks something like a parabola, especially if it's laminar. But what we can do as a simplification is just pretend that it's uniform across the whole pipe, and we'll just use the average velocity then. We'll do that a lot, not always, but a lot. And in that case, we can just say Q equals V times A, M dot equals rho VA. And those are the equations that you had in thermo. All right. So let's do a very simple example with this, kind of like what you had in thermo. And we'll do a few harder examples in class in the worksheets. Okay, so here we've got a water tank. Whoa, seems to be missing. The tank part seems to be missing in mine. But we have an inlet here. We got an exit here. Hopefully your notes, it's not missing. And we got something here. We don't know if it's an inlet or an exit. So I've already labeled these 1, 2, and 3 here, our inlets and our exits. We have an inlet here. We have an exit here. And we don't know if this is an inlet or exit here at 3. And we're given some information too. D1 is 6 centimeters. Q1, 100 meters cubed per hour. D2 equals 5 centimeters, V2 8 meters per second, and D3 4 centimeters. So we're supposed to find, first of all, the volume flow rate at 3, Q3, and the velocity in the pipe at 3, V3. Okay, and what we're going to do is use conservation of mass for this. So solution process on here. First, draw the control volume, label it. Label your inlets and exits, in other words, the 1, 2, 3 up there. List the known conditions and assumptions. Okay, so I already did that for you. Steady state, and these are our simplifications from above. Steady state, fixed number of inlets and exits, incompressible. Okay, so we were just given a V2 here. We were not given that V2 equals U naught Y over H to the 1/7 power like we were before, right? We were just given a number. That means we're going to use average velocity. Okay, so use average velocities, and not given really a temperature in order to find our properties, so we're just going to use 20 degrees C, and that's what we normally use, is either 20 degrees C or 68 degrees Fahrenheit. Okay, so did step 1, did step 2, okay, and then we're going to develop the appropriate conservation of mass equation. Okay, fixed inlets, exits, steady, average velocity. This is like our easiest case. So A, steady state, incompressible, fixed inlets, exits. So basically we can jump right to sum of the m dot in equals sum of the m dots out. And since it's incompressible, that means that we could pull out our rows and cancel those out, and Q in equals sum of the Q's out. Okay, this is the incompressible part. Okay, so one little issue we have here is 3. At 3, we don't know if that's an inlet or exit, so we don't know which side of the equation to put it on. So let's just assume 1. If it comes out negative, that means we assumed wrong. So I'm going to guess that Q3 is an outlet. Okay. If negative, I just guessed wrong. And we still have our answer, just change the sign. or just say, call it an inlet then. Okay, so we have our equation, sum of the Q in equals sum of the Q out. So our Q in, we can just use our subscripts. We can say Q1 equals, and I said Q3 is outlet, so Q2 plus Q3. Okay, or we're trying to solve for Q3, so Q3 equals Q1 minus Q2. All right, so Q1, wait, which one were we given? Q1, 100 meters cubed per hour. So Q1, 100 meters cubed per hour. And you could leave it like that. I'm going to put it into meters cubed per second. 1 hour, 3,600 seconds. I'm just used to using seconds. You don't have to. 0.02777 meters cubed per second. Okay. We aren't given Q at 2. We're going to need it. So we need to find it. We're given V at 2, and we're given D at 2. Okay. D is diameter. So we can figure out from V2 equals 8 meters per second that Q2, since we're using average velocity, we don't have an equation for velocity, is V2A2, comes out to be 0.0157 meters cubed per second, where A2 is pi over 4 D squared. All right, so now, easy, Q3, just Q1 minus Q2, comes out to be 0.0121 meters cubed per second. Okay, and if I want to get that back in hours, 0.0121 meters cubed per second times 3,600 seconds per hour equals 43.45 meters cubed per hour. And came out positive, so I guessed right. It is an outflow. Okay, part B says find V3. Okay, we can use the same equation, Q equals V times A, if we're trying to find just an average velocity. Rearrange, Q3 over A3. V3 equals Q3 over A3. Solve for that, 9.6 meters per second. Okay, again, A3, pi over 4 D3 squared. All right, that's it.